Hello, my name is Julian Peller. I'm a data scientist and a Kaggle Notebook Grandmaster, and this is a hands-on introduction to machine learning. We will cover all the steps that a data scientist takes in order to solve a machine learning project, both fast and in a detailed manner. The idea is to show or present the thought process and the reasons behind each action taken. We will start building some basic models, and in the end we will build some state-of-the-art models. So we will cover all the steps from zero to a reasonable solution to this particular problem. For that, we will be using a dataset from Kaggle named NLP for disaster tweets, and that's a binary classification problem. We will see what's that shortly. So for this first video, we will cover these 4 bullets on my left. We will discuss about the environment, the working environment for Python, and we will discuss about how to download and load the dataset with pandas. We will talk about some basic concepts of machine learning that will help us understand what we are doing, what it means to frame a problem as a machine learning problem. And finally, we will build 2 simple models with scikit-learn on top of this dataset. So let's start. As a working environment, we will use Python 3 and Jupyter notebooks. This is a kind of industry de facto IDE. There are other options. For example, the programming language R is also popular, and some people like to code in IDEs as VS Code and so on, and they apply for some other tasks. But for prototyping and building models, we typically use Jupyter notebooks. We will not cover how to install Python 3 and Jupyter notebooks in this video. We'll assume that you already have those installed on your operating system. You can Google that quite easily, install Python 3 and your operating system. Also, for Jupyter notebook, I suggest to install Conda. Conda is a package manager for Python. It downloads libraries. It handles the task of downloading libraries, and Conda with a basic installation comes with all the data science stack like pandas, NumPy, scikit-learn, and so on, and also Jupyter, that's an IDE but also a Python library. So if you don't have those things installed, please pause the video, Google them, and try to solve that. And I will assume that you're able to run Jupyter Notebook in a specific directory. That's something you might need to Google. In Linux and Mac, it's quite trivial. For Windows, you might need to change the shortcut properties, but you can Google it and it will appear in Stack Overflow. You will find a solution for that in Stack Overflow. So I will assume you are able to do this with me. Create a folder named ML introduction, and I will go there, ML introduction, and I will run Jupyter Notebook from here. Okay, that's loading, and here we are. And this is the Jupyter Notebook root or folder view. And from here you can create a notebook, pressing new, Python 3. And here we have a new empty Python Jupyter notebook. Okay, this is an empty Jupyter notebook. We will put a name. We'll name it ML introduction part 1. This is a file. You can see that here it's a file, or here you can see where we? ML introduction. This is a file. This is the extension of a Jupyter Python notebook. And the basic building block of a notebook is a cell. This is a cell. This is actually a code cell. I will insert more cells. There are 3 cells, 4 cells, that's a cell, okay? And I can turn a cell into a markdown cell. There are 2 types of cell, code cells and markdown cells. You can see in this dropdown, I can change the nature, the type of the cell. A markdown cell is a cell where I can type text. This is text inside a markdown cell. I can run the cell and it kind of stabilizes there as a text. And there are code cells where I can write Python code. And run it, and it will create the output. So the core concept of a Jupyter notebook is I can mix text with code, so I can kind of explain what I'm doing, and that's one of the most interesting things about notebooks that make them so popular in this kind of research or theoretical theory meets industrial world that is data science. So the markdown can have not that rich format, but rich enough. So this is a title. This is italic, and this is bold. How do you know the language for this formatting? You Google markdown cheat sheet and you enter to this one or this one. Both are good. And you can see here, this is great because you can see the code in action. So I will leave it here as a link, markdown formatting language. So this is how you put a link, okay? This is the very basic of Jupyter, but also most of it. It has some, it allows inline charts as well. Import matplotlib.pyplot as plt. Okay, so you can plot stuff and it shows directly. This kind of things make Jupyter Notebook much more friendly for profiling and for prototyping. So for example, this is and for sharing work. So this is a recent work I published where you can see there is you can insert text, format code, inline code, add a video here, embed a video, and then present blocks of code with explanations of what's going on. It also allows to run bash or command line level commands from within with this exclamation mark. So this is the basic of Jupyter Notebook. Let me see. Code, cells, code and markdown. Those are the two types of cells. Then one more thing about this environment. So do you see here there is a green box? This is highlighting the cell I'm standing on, and the green means editing mode. Editing mode means I am typing inside the cell. If I press escape, it turns into command mode and a blue bounding box. So if I press enter, I go again into editing mode, command mode. When I'm in editing mode, I press up and down and I move inside the text. When I press escape and I go to command mode, I navigate through cells. If I press enter, I enter to edit mode again. Okay, so those two modes are the most important ones. You can see here a lot of commands and stuff. So everything has shortcuts here, and they are very useful if you work a lot here. The only shortcut that you must know in any case is the shortcut for run, that is Shift Enter. So instead of coming to the cell and pressing that button, so instead of doing this, I would stand here and press Shift Enter. Then you will see that I will be using a lot of shortcuts. For example, escape DD will delete a cell, and escape B will insert a cell below, and A will insert a cell above. You will see during the video that I code with all this stuff. Also, you can, for example, mix two cells with Shift M, and there are a lot of things that have shortcuts, but you can always find what I will be doing here: insert cells, edit, delete cell, merge cells, and so on. So everything I will be doing, you will be able to find here as a user interface command. Kernel, if you messed up and you lost your variable and you don't know what's going on, you can always shut down the kernel and restart and run all, and it will just start from the beginning and run all the code. Okay, that's it for the environment. Let's see the dataset now. For this tutorial, we will be using data from a Kaggle competition. Kaggle, for those of you that don't know, is the most famous competitive data science platform. It's well known in the community, and it hosts a lot of competitions, most of them with some prices that range from $25,000 to $150,000. And it hosts also getting started competitions like the one that we will going to compete on. This is natural language processing with disaster tweets. There is a data set, there is a task, and there is a metric and a leaderboard where you can check how you perform, how your results perform, and compare them against the community solutions. Don't get scared by these scores, they are fake. We will see that in a moment. So let's start downloading the data. I will share this link with the video. So you would get here. I will create a new notebook, by the way. Download the data. Go here and press download all, and we will store it. ML introduction. I will create the folder data. I will download it here, and I will extract it. Extract here. Actually, okay. So there are 3 files, very small CSVs, and that's the data of the competition. The train data, let's go to see them. This is what the data has. There are some columns that I have hidden, but we will not use them. So this is the train CSV. Ignore these columns for now. It contains tweets and one column with named target with ones and zeros. The target, if the target says 1, it means that the tweet is referring to a disaster. For example, this one refers to wildfires, okay? If the target says 0, it means that the tweet does not refer to a disaster. And the task at hand is to classify them into these two categories. We will build a model, a program that, given a tweet, it will say whether it refers to a disaster or not. That's the task. We will frame it as a machine learning problem, but what we want, the specification of what we are going to build is a box that, given a tweet, will output a 1 or a 0 with some level of confidence, hopefully high, and that's it, okay? And for doing that, we have this. We can build it with other input. We can do whatever we want. And to figure in the leaderboard, we will need to evaluate. This is something I added. This is how the test.csv comes. This is this file. I'm opening here because I don't have Excel right now. So this is the test file. It only has tweets. So what will we do? We will generate predictions for this. For example, just happened a terrible car crash. This could be a 1. Heard about an earthquake. That's a 1. There is a forest fire, a 1. Okay, hey, how are you? This is a 0. Okay, I'm working as the model here. And this is why I told you don't get scared by the 100% score solutions. This is a competition that's running constantly, so people can't just do this, right? So eventually, since there is a time frame, there is no time frame and it has been running for years, eventually someone figured out how to get a 100 perfect submission, but that's not achievable in real life. So that's the train, that's the test, and the sample submission is just how the submission works. So the submission would not have this text, okay, but we'll have predictions for all the text in test.csv. And that's, as you can see, the sample submission has all zeros, meaning the prediction is always, this is not a disaster tweet. That's a basic model, a trivial dummy model. Okay, so that's the task. And that's the data. We will load it with pandas now. Load data. So I will import pandas as PD. This is the how it's done in the industry. If this has it raises an error like this one, import module not found. This means that you don't have pandas installed. You can install it running this pip install pandas. I will leave it here. If you installed Conda and if you installed Jupyter using Conda, then you will have all these libraries already. But I will leave here what we will use. That's it. So if you get this kind of error, one comment about the errors. Typically, the last line is the most informative one. You can Google it and no model name, whatever, and you might find solutions for that. Okay, so we import pandas and we will just load the data frames. Read CSV is the method for that. And that's it. That's the train data frame. with .head, I will show the first 5 rows. One comment is if you get this error, file not found, here is the most important, file does not exist. This means that the file is not in this path. What you can do is make sure you are specifying the correct path. You can check if your Jupyter notebook is. So to do that, you need to see that in this root directory, there is a data folder and there is a train.csv. If that's not the case, one simple solution would be to find out where you're standing. In Windows, this might be different, but in my case, it's this way. So you can put the absolute path to the file, and that's it. Okay. And okay, what else? Let's see the shape. df train shape. It has 7,600 rows and 5 columns. I already said that we won't use these columns, so let's drop them. Keyword, location, I want to make it very easy. And that's it. That's how you drop 2 columns. Axis 1 means columns and axis 0 means rows. And if you do this, you will find out that the change is not persisted. So what you would do is this, right? So you override the variable with the data frame with the columns dropped. That's it. Now it should have a smaller shape, 3 columns instead of 5. And we can see, for example, the target value count. How many targets are zeros, 4,000, and ones, 3,000. We can normalize this, meaning taking the distribution, we can round it, and we know that 57% of the data set is of non-disaster tweets, and 43 is of disaster tweets. Okay, let's load the test data. Same here, we can drop the keyword. And we can check the size. It has 3,000 rows here. Okay, so we will train a model over this data, and we will predict eventually results for this data. And we need to generate something like that looks like the sample submission. It will have the ID of the test row and the prediction for this. So this one should be a 1, and this one should be a 1, and so on. And when we have this submission CSV, we will come here and submit predictions and upload the file and see how it performs. So what I will do now is submit the sample submission to see how it works. So the sample submission is a dummy model that says everything is a 0. Everything, all the tweets are non-disaster tweets, let's say. Okay, it's submitted, and the score here is 57. Where does I already did a submit that scores higher when I was building this tutorial, but you can see that it's the baseline is not a 0, is 57. This is a very dummy model saying everything is a non-disaster, and we need to get over that, get scores over that. One comment is that this 57 is also, it happens to be also the percentage of non-disaster tweets in the training data. So a normal metric used for classification is accuracy, meaning what's the how many rows did I predict correctly. So if the true value is, let's say 1100, and I predicted 1101, I could get a 75% accuracy. It's the normal concept of accuracy. If I predict 2 incorrect and 2 correct, I would have a 50% accuracy. The metric that's used in the competition is not accuracy, but it's an average of precision and recall. I won't dig into this, but it's strongly correlated with accuracy. For this scenario, I have checked that my scores in the local host for accuracy are very, very similar to what I obtained in the leaderboard. So we will assume the leaderboard is based on accuracy. It's not, but it's too complex for an introduction. Just for informative purposes, accuracy has a strong problem, in particular with imbalanced data. For example, if here our data was 90% non-disaster and 10% disaster, a model that predicts, this simple model that predicts everything is non-disaster would have a very high accuracy, and that's kind of bad, right? It's like the metric is not it's not good to determine if a model is good or not. So with that problem in mind, there are some disaggregated versions of accuracy called precision and recall that have a kind of trade-off between them, and there is an average metric for both of them that averages some level of precision and recall. It's called F1. That's evaluated in this leaderboard. But as I said before, we will use accuracy. We will not discuss this further, and we will assume that the leaderboard is very strongly correlated with our accuracy score. So set this, we finish the dataset loading part, and we move forward to some ML basic concepts to understand what we will be doing later. Let's understand now some basic concepts that will help us develop a machine learning model for this task. So we have a tweet right now. I actually will put a box around it. We have a tweet, right? The tweet is something like this. Just happened a terrible car crash. That's the tweet. And we want to assess whether this is refers to a disaster. What happened? Something happened. Yeah. Refers to a disaster and doesn't refer to a disaster. Okay, we need to define if it belongs to one of these two classes. How will we define this with a model? The model will receive the tweet as an input and will output the belonging of that tweet to one of these two classes. Since there are two possible classes, we call this a binary classification problem. This model can be anything that knows how to do this with some level of confidence. I can hard code by hand a model that won't be a machine learning model, but it will still be a binary classification task, right? So one model could be a handcrafted model. If the tweet says has any of the following words, then it's a disaster tweet. Otherwise, it isn't. Where the words are crash, tornado, death, I don't know, a list of words. This is a model, a handcrafted model. Another model could be all the tweets are non-disaster tweets. This scores an accuracy of 57. This is the majority class model, and it's a very strong baseline. So if your model goes below that number, it's very bad. And you can assume this is the 0 line, right? So this is what we would call a normal programming, a normal computer program. We can code it, craft. Okay. Now let's think of this as a machine learning problem. We will, instead of hand coding it, we will build something, a learning algorithm that will output a model. So we will learn, train, create a model, not by hand coding the rules, but by showing the computer with pairs of data. How can I align this? Okay. So this is the training process. How does the training process work? We will have a lot of, what's this? We will have tweets, okay? This is what's called training data. Let's take real training data. So this is one training sample. And we know that it has a target value of 1. Okay, meaning 1 maps to this box. This is refers to a disaster 1. That's that class. Then, come on. Let's say we have 4 training samples. Let's see more data. Okay, everything is a disaster tweet. Here, what's up? I love fruit. This is another training sample. This is a 0. And this is my car is so fast. This is also a 0. And finally, one more 1. Damage in school car is a 1. Okay, this is our training set. We will ask a machine learning model. There are different mechanisms to shape and to consider these tweets and define whether they are disaster or non-disaster tweets. So what the model will learn is this arrow. We will not explicitly code it, but we will tell them, okay, here are some pairs that have this relation. I want you to do your best in order to learn this relation. And there are different models that will approach this problem differently. Okay, we will see two examples. So for example, we can one model will count the presence of different words, and will do some statistics for presence of words in different classes. So maybe in the data set there is a lot of if the word fruit appears, then there is a low probability that's a disaster tweet. It's probably talking about non-disaster stuff. So the model will find those things. Damage might appear a lot in disaster tweets and not in non-disaster tweets. So that's a naive Bayes model. For example, will take some statistics about the presence or absence of some words in different classes, but it will learn it directly from the data. Okay, so that will output a model. What we will do now after is, before taking the model to production, and we want to assess if it's good or not, what we will do is, from our training CSV, we will keep some rows apart. We will keep some rows for which we do know the output. Let's say, I'm afraid we do know the output. This is called the validation set. Validation. This is very important. This is the core, the training process, where we show the model with some pairs of inputs and outputs, and we tell the model, okay, I want you to try to do your best finding this arrow. Then we will hold out from the model. We will not show this model with these samples. And then we will ask the model, okay, give me your predictions about these samples. This is a mechanism to assess the quality of the model, the generalization power of the model. So we don't show the model the output of this. The model hasn't seen this ever, and it will generate some predictions. Let's say the model predicts real value, real target, and this is the prediction. Since the model haven't seen this ever, we can assume that what the performance here is a kind of generalization power. It will give us confidence about the generalization power of the model. Okay, it's important that we don't evaluate the model on the same data we trained it, because it will give us overly optimistic results, because it can memorize the training data. In this case, for example, we would have a 50% accuracy. This is a toy example on validation. This is a toy example which has only 2 samples, but let's assume there are 2000 and it has 50% accuracy. In that case, we will say, okay, this model has 50% accuracy on validation, and that will be a good estimate, or a good, we will have some level of confidence that this model, when shown with unseen data, it will probably perform with that level, or with that metric, with a 50% accuracy. This is the trained validation split. I'm leaving aside few things like hyperparameter tuning, where you need to split train, validation, and a test set. I'm leaving aside the concept of cross-validation. This is just the most basic validation scheme. There are more complex schemes, but this is the core of machine learning. So once we have a trained model and we have validated it and we got a validation score, we will use that model for prediction for example, for the test set and the leaderboard. Okay, that could be the workflow of binary classification task approached as a machine learning problem. So let's build now two simple models with scikit-learn over the NLP with disaster treats. Let's start with the modeling now. We will build a simple handcrafted model using something similar to this idea. We will start with this baseline, full zeros, and we will create some set of words by hand and check the presence of those words, and that will be it. Let's do this, save as image. Now we'll provide the notebooks as output of the pipeline. Part 3, basic model. Let's add the image. I don't remember how to add an image. What I would do is go to one of my notebooks and copy the formats. So notebooks are a common language, let's say. So this looks different, but it's very similar. Everything inside is the same as the Jupyter. So, and the ML pipeline. By the way, this is a superset of, was it a PNG? No. This is a superset of HTML, so you can use HTML here. Right. And I could have embedded the image. Okay, so we will copy a lot of stuff from here. I will call this df because I will split now it into df validation and train actually. So I will start already renamed df. And finally, df submission. That's it. Good. Let's import the accuracy. And okay, so we have our data frames there. Let's do first of all, let's do the train test split. Train validation split. We can do it by hand. For example, let's say we want a percentage for validation of 0.1, then we can PCT val times len df. This will be a floating point. So n val row n val, and we can do iLog till n val till the last n val. This will be df train, and df val will be df iLog from the last n val till the end. and we can wrap up these two thingies in just one line, doing it this way, so it's short and sweet. And let's see the shape of the F train and the shape of the F bar. That's it. So roughly, no, not roughly, almost perfectly, 90 and 10%. So the same can be achieved with, I think, what's model selection, import train test splits. Yeah, this achieves the exact same with test size, PCT bar. Df train 2, df bar 2. So it rounded differently, but it's the same idea. And the F train has this data, and the F bar has this data. We could have shuffled the F before. If, let's see, we can check that it was not, or at least have an intuition that it was not value counts. We can have an intuition that it was not sorted if these numbers are roughly the same. So they are roughly the same. Let's keep it this way, but we could have shuffled it, and here it also has a parameter for shuffling the. I'm inside the parentheses and pressing Shift Tab. If I press it a lot, it will pop out like this, and you can specify shuffle here. All the parameters appear here for every function, right? Okay, let's build this handcrafted model, for which we will use something that's known. We have text, and models are mathematical or statistical entities that require numbers. One way for turning text, there are not that much ways. One way is one of the mechanisms for encoding text as numbers is assigning each word with a number. So, for example, this one is going to be, I keep a dictionary with the mapping, saying this one is word 1, this one is 2, this one is 3, and so on. So when they appears again, I will use 1, 2, 3. I will use put the number 4. There are different ways for representing texts. One is the count vectorization. The count vectorization will create one column for each word in the vocabulary, and will assign to, so I will have the column 6 there. Yes. A cow, tornado, and so on. So this could be columns, and the representation of one tweet here would be the count. For example, let's say this. This is the tweet. The representation would be in this. We'll have 1, 2, 3, 4, 5 coordinates, and the first coordinate says how many times does the word "the" appear in the tweet. That's 1, right? Because it appears here. Now, count vectorizer intuition. Yes, now the second coordinate. Yes, it appears once. Let's assume it's uncased. Ah, it doesn't appear, then it's a 0. Chaos. No, it doesn't appear, 0, and so, and that's it. So a lot of tweets will collapse into this 5-dimension space, and all the tweets will have a representation here. If the word "the" appears more than once, it will says 2, 3, and so on. Okay, that's what the count vectorizer does. And what we will do here is, let's define some disaster words. Let's say pain, injury, trauma. I'm reading there, trauma. I'm reading 2 times. It says trauma. Tornado, crash, hurricane, flood, death. Let's see more. This is a handcrafted model. We can see some more examples here. Fire. Let's assume that if they are talking about a forest, they are talking about. Okay, so let's skip these words and let's build a feature representation for the create features of a given text. We will do this text.lower, and that's T, and for word in disaster words, let's I don't remember this, let's say a.count a. Yeah, so we'll say t.count word. Okay, so create features, let's call this, yeah, that's okay. And I'm in pain because of the tornado match there. So 5, like the mean, okay? And this will be called X, and this will be the tweet. My bad, tweet. Okay, and this is the representation. Let's add one more. So fire around. Okay, it's quite obscure, but it doesn't matter. Okay, so fire up has 2. This is a count vectorizer. Actually, let's model. Oh, I have it here. Let's import it and let's try to build this representation exactly using this tool. So you trust me that count vectorizer this is going to do the same. We'll see how. We need to specify a vocabulary, otherwise it extracts the vocabulary from the data. So the vocabulary is disaster words, vocabulary, and vect.fit transform. You can explore scikit-learn. They offer fit transform for transformers, not transformers, but stuff that modify the input, and then fit predict for the stuff that generates a prediction. So we are expecting this to have I think that a transformation of the input. This is not going to work. I think that I will need to provide a list. Yeah. And vectorizer output to pandas. Since, as I told you, the vectorizer will build the vocabulary from the input, taking all the words that appear there. so that can scale quite fast. So that's why it returns an sparse matrix, because it will be a very, assume you give a lot of input texts, so it will create a lot of columns, but most of the columns will be 0, right? Because you will have a representation where each tweet is represented in all the vocabulary, but each tweet has only few words, so it's mostly what's named as a sparse matrix, meaning there are a lot of zeros, and sparse matrices can be represented as different compressed formats, and that's what's going on here. So this is the sparse matrix, but I don't really care. That's a sparse, because okay. So here we have actually, let's do ilog 0 to dict, and here we have the exact same representation we built by hand. Double check that. That's the same, but it comes with inside of a table, and what you can do actually is put more. The forest was so nice. It's 2, and this scales up with just doing nothing. It worked for more than one tweet. So here we have numeric representations over this set of columns, and that's it. Let's we can do both. Apply the count vectorizer or dftrain.text, apply create features by hand, features by hand. I think that this is going to be a okay. Can I do this? No. Features by hand. I think that I can do this too. List. This will give me a list of dictionaries, and this is something that the data frame constructor accepts. Yeah. So, and the features. So what we can do is actually add dftrain.join dffeatures. That's something. And finally, what we can do is actually build the df features with the with this guy. Back. Let's df train.text x3, and let's get it out again. Df features sklearn. Back to, and that's it. Okay, this should be the same, exactly same as df features. Maybe the columns are in other, I guess they are not features. A lot of truths to verify that they are all truths. You can do, oh. Well, some of them are not. Maybe one is, I don't know. They should be the same. They are probably, let's see where they are. Oh, here, false, false. What's going on there? ilog 3, 5. That's a 0. What about? Oh, this is related to the lowercase. I need to add to the vectorizer something like lowercase true. Oh, this is okay. So let's see what was this dftrain.ilog3. This is probably so this is what's going on. My vectorizer is not considering the tokens, so it's reading this and saying, okay, the word fire appears here, while the scikit-learn vectorizer is considering the full tokens, so it only will count fire if the word fire appears exactly, and it does some pre-processing, but not that much. Here it's what a token is. This is a regular expression. This says it should be the full token with spaces around. So I won't match this as a fire. So, but the idea is the same. It's a different implementation. Let's stick with the. Now that you understood, let's do the jump to the count vectorizer and keep these features, okay? Because I want to show you that we are very close to doing something like this. Vect3. This is not going to have a vocabulary. It will have a max features of 1000. And this vectorizer will generate the features large. My indexing is terrible, but large. This has 1000 columns. Which words are these? The top, the 1000 words that appear the most in the dataset. That's how it decides. There are different mechanisms. You can specify different criteria to drop some words, to drop stop words. For example, let's say stop words English, I think. Yeah, so that will drop the and so on. Okay. And there are a lot of more parameters. You can say, okay, I want to drop, I don't know. You can specify lots of stuff, but the concept is the same as this one. Here we are keeping, let's keep 100 words, because otherwise it starts adding a lot of columns. Columns. These are the 100 most words that appear the most. Note that this is not just for how do you say, disaster tweets. There are a lot of disaster stuff, but you can see that around there is best. So these are the most common words, and you can see that probably this is going to be a great representation, because today video, YouTube, HTTP, I'm trying to find the non-disaster things. I think there are a lot of disaster. Anyway, if there are a lot of disaster words in the representations, maybe a lack of them will be a good discriminator for non-disaster tweets. So let's go to, let's do this. I already did this and already perform it, and I want to undo it. So I need to unroll a lot of stuff. That's it. I will join it with sklearn dftrain. it's okay. So we have this, again, this simple representation with fire, forest, and I don't know, those 10 words. And the vectorizer that generated it was named vect2. Okay. Now see that vect2 was fit, and okay, actually it doesn't matter right now, but it will matter when we build the vocabulary. Here we can fit on the train data, but we cannot, and we can transform it. For the validation data, what we will do is only transform it. We can never ever fit, this is train or learn parameters from a validation data. But we can always apply stuff that we learned from the train data. If we do fit our models with our validation data, what we will do is what's called a data leakage. And our models will be contaminated and our results will be overly optimistic. So this is the vectorization of the validation data. Well, and let's already do it together. df-val.join this. So this is our validation data. We have, oh, what happened? That happened. Oh, the IDs here are, yeah, hold on 1 second. So here it's for train it joined correctly because here the IDs were starting from 0. So I will need to reset the index here. Equals true. Columns over, oh, yeah. Now what happened is that since I performed this, the df-val already has these columns. So I will need to rerun this. This can get quite messy eventually. So make sure what you need to take is as an invariant condition is that if you rerun the full notebook, it should have a run correctly. So make sure that you don't have code that depends on going back in time. Let's say here I'm sure that if I rerun this, I will get, or I'm not sure, but it should be the case. So yeah, we have this representation already, the target, and the same representation for the validation set. We can even build the representation for the test set. What it's going to be submitted, okay? Transform X test. Okay. Now that we have the representations, we said we will build this handcrafted model, but we can fit a machine learning model on this representation already. But let's build the handcrafted model. Handcrafted model over count vectorization, count vectorized representation. The model will be model. We will take a row and we will say for column in, what was the name of this variable again? Disaster words. We can actually do this. Let's rename features equal disaster words. Sample. A sample will be one of these rows, only this part, right? This is one sample. So I will ask sample. If sample subfeature is not 0, then the model will return a 1. Okay, if any, this means is if any of these numbers is not 0, then this is a disaster tweet. If all the 4 goes and no feature was on, then it's a not disaster tweet. And let's do that. Let's prediction. So the prediction is everything is a 0 and prediction equals df train.apply model. I think that I need to specify axis 1. This is not necessary. No, it's not axis 1. So this will apply. Let's see. I'm not sure. Key error pane. How come? Oh, I didn't do something. No, this. Oh, I did it, but then I reset the thing for the validation set. Okay, so now we are cool. We are good. We should be good. That's that. So, yeah, here we have our predictions on the training set. That's our model. Let's see the head, for example. So, our model says that almost everything is all these, since they don't have the any word, there are no disaster tweets, and this is a disaster tweet because it had fire and forest. Okay, and we can now evaluate the accuracy on the train set, which will be, in theory, if the model were trained, this could be overly optimistic, but we didn't train a thing. We just represented the words, the tweets, and we applied the model. So since most of them will be zeros, but some of them will be ones, and we know that the all zeros is a 57%, I'm expecting this to be a little bit higher than 57%. I don't know, but I'm expecting, since this representation should be quite accurate in the sense that if these words are present, it's probably a 1. It should increase the accuracy from 57 a little bit. Okay, 3% more. We can do the same for validation. And we can calculate the validation accuracy, which is 57. Okay, so here it didn't improve. Maybe it was too simple. Okay, let's add some more words. Let's do this. df train. No, let's do this. Let's build a. Let's do the same, but with another. With a larger vocabulary. Okay. Let's do. Let's submit this. So, test.apply model axis 1. We'll call it target, and we will get Then we have the target and the ID. The submission has this format, so we will keep ID and target and dump to a CSV, which will be named handcrafted model.csv index false. We drop this first index, the 0, 1 at the beginning, and that way we saved this data frame to disk. And let's submit it to the competition and see how it goes. Submit predictions, ML introduction, handcrafted model. That's uploading, and that's it. Make the submission. We can expect to have some result between the train accuracy, that again is not overfitting because we didn't actually train on the data, and the validation accuracy, which was 57. So we got 59. We obtained 2 points with this very simple representation. And the next model we will build is builds on top of the same representation, but we will scale up the vocabulary. We will actually use what we saw previously here somewhere. This kind of representation, we will scale this up a lot, and instead of having this simple rule, we will build more complex rules, and actually we will delegate the building of these rules to machine learning models. With this count vectorizer and a very simple probabilistic model named naive Bayes, we will build already a very well-performing model. That's not the state of the art, but it's the strongest baseline with simple models. That's the next step in this tutorial. So we got our first handcrafted model. What I will do now is collapse all we have done here into one notebook. I think that the concept we applied here was smarter than it looked. Only that the amount of words we used was too small. So I will just wrap up everything so we can apply this in a faster way, and we can try the same concept with a lot of words. And after that, we will move to not specifying the vocabulary, but getting it as we did in the here, sometime here, here. Max features equals. It's bad. We will parameterize the count vectorizer so we can play with it easily. Okay, so I started this notebook. This notebook is wrapping up stuff. Here, this is loading the data frames. See, this is the beginning of the previous file, and it's doing the split. So here I will return df train, df file, df test, and df sub. And actually, I was going to put here where both equals true, and here if where both print train shape and train val test. Okay. Now we can load the data frames very easily and parameterize, for example, the size of the validation set. Okay. What else? So we have this. Let's put a title here. After we do this after we parameterize the count vectorizer and we show that this concept is much better than just 2% of score, we will move, do a little improvement there, and we will achieve a very good score. So let's do this. The count vectorizer pipeline. This could be df count pipeline, where we will receive df train, df val, df text, and what will we do? And the vectorizer. So the vectorizer is a parameter. It does bit transform, train, df features. Let's do this. Train goes here, vectorizer goes here, and now train is that. Now the same for validation. Well, vectorizer only transform, the same for test, and test, and that's it. That's applying the vectorization to all of them, and then we have a model. We'll parameterize the model, model function, let's call it that way. And the model function will receive this will be one function, which will be handcrafting model, which will receive a data frame, and it will so let's say we have these our words. How can we do this? We have these words. We will expand this, but disaster words. Our handcrafted model will be this. Where was it here? This is for one row. Model of data frame will be df under. It will return the predictions as df underscore text dot spring dot lower dot apply model. This one. This is white bread, and what I'm doing? No, this is we'll apply the model and we'll return a 1. Yeah, return white bread. So this is taking the text. No, this is not correct. This is correct. Because we already have the vectorization done before. Here. And here and here. So this is the handcrafted model. And here we will call, let's get one of the count vectorizers of this one. And so we could call this with the vect and this function. Okay, and then with this function we will apply the model function to df feature train. This will give me y prediction for train, The same goes for validation and for the test set. Val test. And now I can compute the accuracy score in df_train underscore target against y_train. This is train accuracy, and not twice, just once, because for test we don't have an accuracy at all. Well, so let's print it. Print train accuracy, train arc with just 2 decimals, and validation accuracy with 2 decimals as well. And that's that. Now we want to return a submission. So that could be y test predictions underscore target equals this df test id comma target return. Okay, this looks pretty functional. And that's that, and that's it. This would be submission. We have count vectorizer it's not, you're right. It's not defined. Now it's okay. See that we can copy all this stuff. Actually, these two might go like after, because this is like solid code, and this is more like code I'm working on now. And let's see what failed now. Features is not defined. Yeah, you're right. It's named disaster works. Okay, here we are. This is a 60 and this is a 57. Let's add one more decimal. It's the same amount of this number of decimals. Okay. Okay. So now what we can do is just change the. See, here we are using. This is a global. Sorry. So the full pipeline only runs. This is a global means that it's used in this function. So if I define this variable after, so we can do this. df_train such that target equals 1. df_train. So we keep all the disaster prints, and we keep the text, and we turn it into lowercase, and we split it into sentences, and we turn this into a list of lists, and we Google how to flatten a list of lists in Python, as we always do. And we have this, and we paste it. Def flatten return. This will make sense in a second. From collections, import counter. Okay, to list flatten. This is the full vocabulary with the train vocabulary with everything repeated. Training words all together in one big list. Training. Actually, let's see this. So you can see this is a flat list of all the words. Okay, what I will do is put this into a counter. A counter is a data structure of Python that counts stuff. So it will give us this dictionary with the keys and the values. For example, we can do this, and better we can do most common 50. Those are a lot of stop words. I will import. You don't have NLTK, you need to do that. From nltk.corpus import stop words NTLK, no, NLTK, natural language toolkit stop words dot something dot words, which, yeah. So let's exclude this from get words from the. This is something. Dot stop words equals true if dot stop words L if dot stop words for W in L if W not in that. And in case this takes complete time, let's define it. So that's L and return L. And keep only alpha. It's true. Keep only alpha will drop and not keep only alpha, or W is alpha, meaning it's alphabetic character and it doesn't have punctuation and so on. So this is if this is false, then all this is true, and otherwise this applies. Okay, get the words. That's it. And this does not. Okay, and actually let's call it get vocab and do the count. So this is now named V disaster and V disaster but most common 200. Okay, let's do this. Let's most common 20. So I will just add them here. Suicide. Fire is already suicide. Killed. Police. And I will not put California. Disaster. Train. That's awesome. Emergency. Bombing. Let's put bomb. Oh, there is bomb. Families sound like burning. News. Okay, let's just try how it works here. Okay. Okay, so we got 5 points more there. That's good. I want to show that this is a reasonable approach and to CSV. So if it has to CSV handcrafted to CSV index was false, and let's actually add it here. Create submission equals false, and I will do if create submission is not false. Yeah, actually this is if create submission is not false, I will use this as the CSV. This part of the CSV. Okay, and this is this guy. Okay. So now we can just do comma create submission and crafted. Okay, let's add a few more words. Bomber, atomic, Hiroshima. It's a disaster. Still, fatal, nuclear, accident. Oh, this will skyrocket the accuracy. Accident. Okay, let's see how it goes. That's good. Let's submit this. Let's submit this and see how it performs here. It's still not going to be a bad one, but it should increase 5 points. And just okay, 65. We already got a test. Score equals. Okay, now. So I'm ignoring few words here, right? And actually, what we could do is normal. We can get this. This will be the normal vocabulary, most common. Normal meaning non-disaster tweets. And we can also get the full vocabulary this way. Oh. Oh, diff. So let's say, okay, we will take all these most the most important words here. The most important, most common 100. Some of them will signal disaster tweets, some of them will signal the others, and some of them will be shared in both classes, right? So what we could do is, here we are defining the model. Is I'm highlighting the words that appear in the let's actually keep this a little more. Accident, storm. Let's increase the score a little bit more. Storm, homes, attack, forest is already there. Car, okay, there. War, severe, oil, fires, army. Okay, let's see this. Handcrafted. Okay. Duplicated. Okay. That is twice. Okay. Let's see. We see that we have a reasonable. Let's submit this to. It's upload already. Yeah. It. Okay, so let's go to the speech. So what we can do, instead of selecting by ourselves the words that are disaster-related words, what we can do is get all important words and tell a model, find the impact the presence of this word has on the output. So I will tell the model, get one weight, assign one weight to the word suicide. If you assign, for example, let's say, if you assign 1, this means it has a strong positive impact on the outcome, on the fact that the tweet is probably a disaster tweet. Okay, if it says sunny, let's say, it has a -1, meaning this has a strong impact in the direction of having of the non-disaster. Okay, this is what logistic regression does. It is a model that assigns to, so we define, first of all, we will use the same vectorizer. No, we won't. We will use this vectorizer over import logistic regression. It's very similar to a linear regression. What we will use is, as vocabulary, we will use the V. This is the words not only of disaster, but in general, the most popular 200 words, okay? So there is, for example, like, we can say it will have a negative weight, okay? This will have a near zero weight. This will have a positive weight because it will impact in the direction of disaster. This is a disaster one. This is a non-disaster one. Video is a non-disaster one. Okay, let's do that. So for WC, the word on the counter in the most common, keep the words. So actually, let's say n words. I pressed insert by mistake. Word, top n words. Okay, so we have the top n words in the full training set. And what we will do is tell the count vectorizer, this is you need to represent the data set over this space, the space of the present or absence of these 200 words. By the way, let's see how it went. Okay, 67 already. We improved 10% from the naive, super basic majority score. Okay, and we are almost here to this one that was using a model. So okay, so that's our vectorizer. This is called vectorizer top n, and as a model we will use the logistic regression, and I will modify partially this. I want to get a lot of stuff. Okay, this pipeline is good, but I want to get the model again. So that's something that is not contemplated here. So let's do this. I will create a pipeline v2. So pipeline v2, which will receive a model, and this is what will happen. So let me show you how a model works. This is a model. A model is fitted on a training set. The features, this is the text or the numeric representation of text in our case, and the target, that's the Y. It's a common practice in machine learning to call X to the features of the samples and Y to the target. Okay, so a linear regression will fit. I will show you. This is a very simple linear regression. These are the features, and the Y is going to be, for 1, it's going to be 2. So the relationship we are trying to predict is 1 goes to 2. The feature 1 has an output of 2. The feature 2 has an output of 4. The feature 3 has an output of 6. I hope you are following me here. The feature 4 has an output of 8. Okay, the relationship is times 2. And linear regression is a model that only knows those kind of relations times something. So here we are fitting that model, and I can predict now with that model. So now I can tell, okay, I want to know what will happen. What could you predict for 5. It should predict 10. Okay? And why? Because it fitted the parameters, the parameter coef, that is 2. A linear regression shapes the relation between inputs and outputs as y equals coef times x plus bias. Okay, the bias in this case is what is the bias? Intercept. It's almost 0. Okay, so that's one example. We can create another linear regression and put a bias in our example. Let's okay, 2 goes to 2, 3 goes to 4, 4 goes to 6, and 5 goes to 8. This should have a bias of plus or minus 1, minus 2. Let's see. I only added 1. Okay, yeah. So I'm quite confused here. I was expecting it to be so minus 2 plus 2 is 0. This is not correct. Six should go to 10, right? In my form. Yeah. So this would be m2.intercept m2.coef 6 plus, yeah, okay, that's okay. And okay, so that's how a linear regression works. Logistic regression is the same, but the output, instead of the impact of the coefficients, is not linear over the output, and the output is restricted to be between 0 and 1. It's a probability of belonging to a certain class, but still it will have one coefficient for each input. In this case, there is only one input feature. If we have more than one input feature, we will have more than one coefficient. So I will delete this. Anyway, what I wanted to illustrate was that I will do this. Model.fit df features train df train under target. This is the fitted model. Now I can predict on the features. This is widespread train. I can predict on the validation, and I can predict on the test set. All the rest is the same, and what I will do is return the model. Okay. So now what we can do is the vectorizer, the model named where it's logistic regression. I will call it M3. I want to observe how it is after applying it. I will create a submission, logistic over, and let's obtain the one of the features also, logistic over 200 of. So here I will get M3 and BF prime. Okay, that's it. Name logistic regression. Okay, so here we have a little better accuracy. I want to show you that here we have coefficients. How many coefficients will we have? 200. One for each word. And we can actually do the feature frame. So this is the representation of the over these 200 words. What we can do is for the columns, we can zip this with the coefficients. So this will be the columns with the weights. And we can create a data frame with columns named feature and weight. Well, that's not good. Coef, I think it's it. Okay. So yeah, the coefs are nested in one. It doesn't matter. So let's see. Sort values by weight. And we can get the head. These are the 10 words that impact the most in the direction of non-disaster. And these are the 10 words that impact the most in the direction of disaster. Okay, so the model discovered which numbers it should put in here assigned to each word to better discriminate between disaster and non-disaster tweets using this representation. That's logistic over. Let's do a logistic over more words, because I'm pretty confident that more words will get us a better result. And words 500. So n words, let's call it n 500. Maybe I'm breaking the. Let's get the top one. Okay, see that it just gets better, but the concept is the same. Let's put so I will just ignore and words, and that's a ceiling. It seems that it stopped improving accuracy. Let's submit this. I will submit the one that had the best validation accuracy, okay, which is this one. See that the training accuracy keeps improving, but the validation accuracy started to decrease. That when that happens, it means that the model is overfitting to the training data. It's getting very good. It's being able to explain the training data with a lot of detail, but it's too much detail. It's just explaining that piece of data, and it's not able to generalize to. Oh, I forgot an F here. It's not able to generalize to better to other. Okay, this one went well anyway. So I will submit this, because although it's overfitting, it improved the validation score, so I don't care. Okay, 79. 79 is already, so the real scores, all these are fake scores, handcrafted. This is probably handcrafted as well. This is a reasonable score. So we are already 5% of distance to a reasonable high score with this idea. Okay. Let's see. Let's do this with the new stuff and see this. These are the most the words that are more important in the direction of disaster, and these are the words that are more important in the direction of non-disaster. So how there is not a linear impact on the output. The output is going to account for all these numbers, and somehow they counter one another. So if I have storm and I have the word better, that will kind of compensate. That's how logistic regression works, but not exactly. They will somehow compensate. It's not a direct subtraction. Okay, the impact is not as in the linear model where you have this has an increase. The coefficients in the linear model is linear, meaning a change in the input of 1 impacts the size of the coefficient on the output. Here is different, but it's in the same concept. Finally, we can put, I will put one more model, naive Bayes, which is the one. We can do 2 tweaks. I will do 2 tweaks, and I will explain them just very in a high level. But these 2 tweaks, TF, IDF vectorizer. Let's start with this. Logistic regression, TF, IDF. Let's submit this. How many submissions do you still have? I don't want to take all of them. You have 2 remaining. Okay, let's submit this. It didn't improve. Okay, it doesn't matter. So TF-IDF, it's a mechanism, a smarter way to count words. Instead of counting the number of times a word appear, counting the number of times a word appear in a tweet is very prone to highlight common words like they, I, you, and so on. Those are words that are going to be very common and will appear a lot. Okay. And a lot of tweets will have a high number on that dimension. TF-IDF is a mechanism to count words in a tweet that's going to reduce the weight of very common words and highlight the weight of uncommon words. Uncommon words that appear a lot in one tweet and not in the full corpus are going to be highlighted. So they will appear a lot in the sample, but as it also appears a lot in the full corpus, it's not relevant. So TF-IDF, actually, now that I think about it, it's more important in longer corpus, longer document corpus with longer documents, because that way you can highlight that, for example, one document is of one field while other one is of another. Okay, so that didn't work. The other thing that I want to do is use naive Bayes from sklearn.bayes import. What was the name? I don't remember. Oh, I typed word. Multinomial. This is a multinomial. Okay. Multinomial. Or hold on 1 second. Word count. Yeah, multinomial. Okay, let's try it and explain it later. So this is with the pipeline we have. I will go back to the count vectorizer to discriminate the impact of each. So, yeah, okay, let's try it on the leaderboard. The scores are kind of plateauing here, which is a kind of high plateau for the type of models we have. And be 5,000. Okay, 78. All are along the same line. Okay, naive Bayes, by the way, what's doing is learning. It's based on the Bayes rule, and this is the Bayes rule. Okay. Can I copy it? I would love to get the LaTeX code for this. Yes. This is LaTeX. It's LaTeX. So this is the naive Bayes rule. The Bayes rule. Where was I here? This basically, it's very important in the statistics because it creates a relation, a link between one conditional probability and the opposite. So if let's put it in terms of if what I want to know is the probability of disaster given this tweet, this is the model I want to learn. The model I want to learn is this. The probability that a tweet is a disaster tweet. Sorry, this is what we are trying to learn. This allows you to recompute it as the probability of this tweet. Given that it's disaster times the probability of disaster divided by the probability of this tweet. So this is the Bayes rule applied to this concept here. Okay, this is the Bayes rule applied to this problem. This is what we want to learn, and we can say, okay, I can model it as this. Okay, so what we are going to do is we will take a few steps here. We will remove the equality and say it's almost equal. It correlates, it scales, it's monotonically increasing and decreasing, dropping this probability. Okay, this is the step 1. Why did it? So let's see. Bar prop 2. I think it's bar prop. It's proportional to bar prop 2. Let's see if this works. on? What's going on? I deleted something by mistake, and I don't know what it is. Oh, yeah, no. Okay. Okay, so we will say this. So we will be able to model this probability as proportional to this. We will actually model this probability and this probability. We'll model both as non-disaster and the probability of non-disaster. Okay, so as that that term dividing appears in both, we can drop it in both cases. It's difficult to calculate because it's the probability of the tweet on the corpus, and that's difficult to calculate, but we will calculate both probabilities, and we will assign the class that has the higher probability. That's what this classifier does, okay? So the probability of disaster and the probability of non-disaster is just this. Okay, that's how it's calculated, and we can check it because here it's going to be its class prime. I think it's storing it as a logarithm for some, yeah, import numpy, smp, and v.x. So there are those numbers, see? This is the class prior. It's stored as a logarithm because of numerical stability. All this can be, instead of calculating the probability, you can calculate the log probability, and some products that will appear soon will turn into summation. Okay, so now we will. That's a good mathematical step, and this is already taken into account. And what we will do now is discuss about this. And here we will introduce the naive hypothesis, let's say, or the naive concept. The naive concept will say that we can model, so this is equal to the probability of a sequence of words, given that's probability of tweet words, and we will shape this as a naive, assuming that the probability of each word is independent of all the others. Okay, that's the naive. I'm calling it. I'm calling hypothesis, but it's not an hypothesis. It's the naive. Yeah. Anyway, the naive assumes that they are mutually independent. So we will say that the probability of the full sequence, that is the tweet, the probability of that tweet given the class is the same as the product of the probability of each word given the class, and the probability of each word given the class is something that we can calculate. It's the probability of a word given a class. That's probability of a word given disaster. And that's something that we do have from the data. Okay, so that's going to be the coefficients. The coefficients probably are yeah, they go in this direction. I'm not sure about the exact values, but let's see. This looks like a probability. Let's see without the exponentiation. Yeah, so this is a log prob, and this is a probability. So what we can do is actually see the probabilities that naive Bayes has estimated for this. See, this is a very fast frame volumes word I missed one, but no, what's missing? Zip takes no keyword argument. What are you talking about? Oh, I missed one point. Sort values by product head 10. So those are the words that are less probable to belong to disaster, the disaster class. Since it's a binary, I said we will model both, but since it's a binary classification, the model can work with just one estimation of the probabilities, and this is the other. Okay, this is the probability. If the word fire appears, then it's a 0.5 chance increase in belonging to a disaster field. Okay, so we covered a lot. This kind of approaches, working with a representation, a numeric representation based on the count and applying a simple statistical or linear model, is what's called the old school approach. It always has reports a good baseline with not that much work. Actually, right now there is a competition here, competition for a prize, where there is a discussion between BERT and TF-IDF plus REACH. REACH is a slight modification of the logistic regression, and BERT is the state-of-the-art model for NLP. So in this specific competition, where there is a price of in total $50,000, linear models, this is a count vectorizer plus a logistic regression, is performing very good. Actually, here I published one work. Where is it? And well, this is something of a incredibly, this is a notebook I published, incredibly simple naive Bayes that's TF-IDF vectorizer without a parameter at all, multinomial naive Bayes, and this scored very good. So this is something that's important. The next step will be to build some transformers, or not build, use some transformers. With that, we will increase our score in the 4% that is required from where we are to the top scores for this competition. So this is basic NLP. This is a way for framing this. The attention models we will see in the next video are more complex in their internals and their nature, but the process for building them is not much more complex than the one we just covered. I will add these notebooks attach these notebooks somehow to the video in the description or somewhere, so you will be able to reproduce all this. And I hope it was informative